Imagine a place in the cosmos, a region of absolute and eternal night. This isn't just darkness between stars, it's where space and time are twisted into an inescapable pit. Light itself, the fastest thing in the universe, is swallowed whole if it ventures too close. Anything crossing its threshold, asteroids, planets, even stars, is pulled in by a force beyond comprehension. It's a cosmic waterfall with no bottom, a true point of no return. These are not fantasies. They are real, lurking in the centers of galaxies and wandering the void. Here, the rules of physics are stretched to their breaking point. Time behaves strangely, and space pulls everything toward a single infinitesimal point. Matter and energy are crushed out of existence, lost to our universe forever. We call these objects black holes. They are black because they emit no light, and holes because nothing escapes their pull. Black holes are the ghosts of massive stars, the engines of galaxies, and one of the greatest mysteries in science. To understand them is to push at the very limits of our knowledge. The universe has its shadows, places of profound darkness as fundamental as the brightest lights. Black holes challenge our intuition and force us to reconsider reality itself. They remind us the universe is far stranger and more mysterious than we ever imagined. Our journey to understand them is one of science's greatest adventures. How does such an extreme object come into being? A black hole is born from the death of a massive star. Imagine a star many times more massive than our sun, burning ferociously for millions of years. In its core, nuclear fusion creates outward pressure, balancing the star's immense gravity. But this balance can't last forever. The star eventually runs out of fuel. When fusion stops, gravity wins, and the core collapses with unimaginable violence. This triggers a supernova, an explosion so bright it can outshine an entire galaxy. The outer layers are blasted away, but the core keeps collapsing. If the star is massive enough, nothing can stop gravity's crush. The core is squeezed into a region of zero volume and infinite density, a singularity. The laws of physics break down, and a black hole is born. Its gravity is so powerful that not even light can escape. The star is gone, but its gravity remains, concentrated into an infinitesimal point. This is the birth of a stellar mass black hole, a silent, invisible remnant destined to wander the cosmos. A permanent scar on the universe, marking the death of a giant. To understand a black hole, we must dissect it. At the center lies the singularity, a point of zero volume and infinite density where physics breaks down. All matter and light that falls in is destined for this incomprehensible point. Surrounding the singularity is the event horizon, the point of no return. It's not a physical surface, but an invisible boundary. To escape, you'd need to travel faster than light. Anything crossing the event horizon, light, matter, information, is trapped forever. From outside, we can never receive any signal from within. Many black holes are surrounded by an accretion disk, a swirling disk of gas and debris heated to millions of degrees. Friction in the disk causes it to glow intensely, emitting X-rays and other radiation. Paradoxically, the region around a black hole is one of the brightest in the universe, even though the black hole itself is perfectly dark. The singularity creates the immense gravity, the event horizon defines the black hole's size, and the accretion disk announces its presence. By observing the light from matter being destroyed, we learn about the darkness doing the destroying. It's a beautiful cosmic irony. The brightest light reveals the deepest darkness. These three components create the phenomenon we observe as a black hole. The idea of an object so massive that even light couldn't escape dates back centuries. In 1783, John Michel proposed dark stars using Newton's laws, reasoning that if an object were dense enough, its gravity could trap light. The idea was forgotten until the early 20th century, when Einstein's general relativity redefined gravity as the curvature of space-time. Carl Schwarzschild soon found a solution to Einstein's equations, describing a singularity and a point of no return, the event horizon. At first, most physicists thought this was just a mathematical oddity, but in the 1960s, discoveries like quasars and pulsars revived interest in gravitational collapse. Scientists like John Wheeler, who coined black hole, and Stephen Hawking showed these objects were an inevitable outcome of massive star death. What began as a speculative idea became a cornerstone of modern astrophysics. How do you find something invisible? Astronomers look for the effects of a black hole's gravity on its surroundings. In binary star systems, if a visible star orbits an unseen, massive partner, a black hole is the prime suspect. The accretion disk's X-ray emissions are another clue. X-ray telescopes scan the sky for these brilliant flickering sources. At the centers of galaxies, astronomers track stars whipping around invisible points at incredible speeds. In our Milky Way, this led to the discovery of Sagittarius A*, a supermassive black hole with the mass of 4 million suns. In 2019, the Event Horizon Telescope linked radio telescopes worldwide to capture the first image of a black hole's shadow in galaxy M87. For the first time, we had direct visual evidence of an event horizon. The black hole itself is dark, but its effects are among the brightest in the universe. We had finally seen the unseeable. What would happen if you fell into a black hole? The experience depends on its size. For a small black hole, tidal forces would stretch and tear you apart, spaghettification, before you even reached the event horizon. For a supermassive black hole, you might cross the event horizon intact, unaware you've passed the point of no return. No force in the universe could pull you back. Your fate is sealed. To a distant observer, you'd appear to slow down and fade away at the edge, never quite crossing. But in your own experience, you'd cross the horizon in finite time and continue inward. Inside, all paths lead to the singularity. Space itself flows inward faster than light. In seconds or minutes, you'd be crushed at the center, where the known laws of physics end. It's a one-way trip into oblivion, a silent plunge into the greatest mystery of the cosmos. No one can return to tell the tale. The black hole's heart remains forever hidden. Black holes are a playground for speculation and science fiction. Could they be gateways, wormholes to other universes? The math allows for it, but reality is less forgiving. Most wormholes would collapse instantly, and the journey would be lethal. The idea remains fiction for now. There's no evidence for such travel. Another mystery is the information loss paradox. Does information that falls into a black hole disappear forever? This pits general relativity against quantum mechanics, suggesting our theories are incomplete. Solving this paradox may require a new, unified theory of gravity and quantum mechanics. Black holes are the ultimate cosmic laboratory for testing the laws of nature. Not all black holes are the same. Astronomers classify them by mass. Stellar mass black holes formed from supernovae are the most common, with masses a few times that of our Sun. Supermassive black holes, millions to billions of times the Sun's mass, lurk at galaxy centers and shape their evolution. Intermediate mass black holes, the missing link, are rarer and may be seeds for supermassive ones. Their origins are still a mystery, but new candidates are being found. Finally, primordial black holes may have formed just after the Big Bang, possibly as small as mountains but denser than anything else. We have no direct evidence for them, but they could help explain dark matter. Each type offers clues to the universe's history and structure. Black holes come in many forms, but all are cosmic enigmas. Are we in danger from black holes? Thankfully, no. The nearest is over 1,500 light-years away. Our galaxy's supermassive black hole is safely distant, and the odds of a rogue black hole passing through our solar system are minuscule. So why study them? Black holes are the frontier of knowledge where the laws of nature are pushed to their limits. They test our theories of gravity, space and time, and matter in ways impossible on Earth. Black holes force us to confront the biggest questions in physics, like the information loss paradox. Solving these mysteries may require a revolution in our understanding of reality. They are central to the evolution of galaxies and may even help explain dark matter. In the end, black holes embody the spirit of scientific inquiry, a profound mystery and a challenge to our imagination. They remind us the universe is stranger than we can imagine, and each discovery is a testament to human curiosity. Black holes are both an end and a beginning, the end of matter and the start of new understanding.